My name is Fossil, and today we're answering the question, how do SSRIs affect serotonin? This presentation is going to be divided into two parts. First, we're going to get into what is an SSRI and what is serotonin. We'll define these terms and their interactions to answer our question, how do SSRIs affect serotonin? The second part is going to give us a chemical basis for these interactions. We'll focus on how chemical structures of molecules underlie the specific interactions between neurotransmitters and receptors, and how scientists can alter molecules for desired effects. If all of that sounds like a lot, don't worry, we're going to break it down step by step. So, to get started, what I'm showing you here are a few advertisements from the 1970s for a drug called Prozac. It was a household name, almost like Tylenol, and it was said to decrease anxiety. It would help you feel more like yourself. You would feel more relaxed, improve your sleep and appetite. It would give you a better mood, and it would regulate your emotions without any known side effects at the time. It almost felt like a miracle drug, and everyone was taking it. It was so easy to get that you could go to any pharmacy, drugstore, gas station, and pick up a bottle of Prozac. Prozac is just one example of an SSRI, which stands for Selective Serotonin Reuptake Inhibitor. Now, what is serotonin? Serotonin is a neurotransmitter. It's also known as 5-HT. Neurotransmitters carry information from one neuron to another. It's how our brain communicates different cell signals. These serotonin molecules can be found within neurons and within the synaptic cleft. The synaptic cleft is the area between where information is passed from one neuron to another. Now let's look at how serotonin moves. In response to some kind of stimulus, serotonin is going to be released from neuron A into the synaptic cleft, and it's going to bind to a membrane receptor on neuron B. And that is going to start some sort of cell signaling cascade in neuron B that will then go to neuron C, D, and so forth. Now, one thing to note is that neuron A has a protein called SERT, and that is responsible for removing the released serotonin from the synaptic cleft and retaking it for later use. Serotonin molecules require quite a bit of energy to make, so it's very efficient for the cell to take up and recycle the serotonin molecules as much as possible. Therefore, as soon as serotonin is released into the synaptic cleft by neuron A, the SERT protein on the neuron A is going to start removing those serotonin molecules from the synaptic cleft within milliseconds of release. So now let's talk about how depression is connected to serotonin, and then we're going to tie everything together. Depression is thought to arise from low levels of serotonin. In other words, neuron B's membrane receptors are not receiving enough serotonin from neuron A. Now, you might be able to think of many solutions, like, for example, increase the number of membrane receptors on neuron B to be able to catch more serotonin. Another solution, and this one is more relevant to us, is to disable that SERT protein that's on neuron A for a longer period of time so that the serotonin that's released remains in the synaptic cleft longer and in higher concentration, allowing neuron B membrane receptors more opportunities to bind and carry on the cell messaging. That's exactly what SSRIs like Prozac do. Prozac, another name for it is fluoxetine, binds to the SERT protein on neuron A and will disable it, basically by taking up the space that was there for serotonin. This allows serotonin that's released into the synaptic cleft to remain there longer, providing neuron B membrane receptors the ability to bind to serotonin and pass on the messenger. So how do SSRIs affect serotonin? SSRIs are serotonin agonists. What that means is they increase the effects of serotonin by disabling serotonin reuptake, doing so by disabling that SERT protein. Therefore, they increase the concentration of serotonin in the synaptic cleft available to bind to neuron B receptors. And that's also why people who take drugs like Prozac and different SSRIs feel better, they feel happier, they feel more alive. SSRIs have become a frontline resource to fight depression. Just to drive everything home, the red transmembrane proteins we see highlighted right now, those are membrane receptors on neuron B. Those are going to bind to serotonin. And as you can see, there's serotonin that's already been released into the synaptic cleft, and those are those yellow molecules, and they're binding onto those transmembrane proteins. But as we just saw, that white protein is the SERT protein on neuron A, which is reuptaking serotonin. So as we just saw, a yellow molecule was just taken back into the previous cell, and that is the SERT protein. The SSRI Prozac binds to the SERT protein, blocking the ability of serotonin to bind to the SERT protein and be reuptaken by the SERT protein. Therefore, there's more serotonin, more yellow molecules in the synaptic cleft, and that allows the transmembrane proteins to bind to them more. So now let's look into the chemical basis of these interactions. There's 3 pieces of relevant information here that connect back to General Chemistry 1. First of all, ions and ionic concentration. What we didn't see in the previous animation were all the ions that occupy the synaptic cleft. We have sodium plus, chlorine minus, calcium 2 plus, etc. Not only do they interact with cell membranes physically, as we'll see in a short bit, but they also create electrochemical gradients that power the molecule transport across the membrane. How does neuron A release serotonin into the synaptic cleft? Well, it's through the electrochemical gradients that are created by, for example, having a lot more calcium 2 plus outside and having a lot less calcium 2 plus inside. Therefore, calcium 2 plus wants to get in, and that movement will eventually, after a cell signaling cascade, push serotonin out. We also have relevance here by molecular structure and shape. Serotonin only fits in serotonin receptors on the receiving neuron. The receptors and even SERT proteins require an exact one-to-one shape with the same molecular structure and charge distribution. Any differences and the protein will not fit, and therefore it will not have the effect that we want it to have. And finally, it's relevant in the polar and nonpolar molecules. Polar molecules will bind to specific transmembrane proteins, and nonpolar molecules diffuse across the cell membrane and bind to internal cell receptors. The cell membrane does not allow polar molecules to diffuse through due to their size, shape, and charge, and must break their interaction with water before they can diffuse through that hydrophilic membrane layer that's inside the transmembrane. The enhanced specificity of binding sites on the membrane, not only of the membrane receptors but also of the SERT protein, highlights what we learned on molecular structure as well as polar and nonpolar molecules and charge distribution. But we can take it even one step further with the help of chemistry. Ions are going to do more than just create the concentration gradients we talked about in the last slide. The synaptic cleft is full of different neurotransmitters like serotonin, but also different ions. In order for the SERT protein to begin the uptake of serotonin, it must first bind with both sodium plus ion and a chlorine minus ion from the synaptic cleft to undergo a conformational change that will open the protein to begin accepting serotonin. And much of that conformational change has to do with the different charge distribution that the two ions introduce. Prozac will bind exactly to SERT proteins and block serotonin reuptake. However, changing just one or two different functional groups of the Prozac molecule can make it a norepinephrine reuptake inhibitor, an NRI, and it will no longer block the SERT protein. Scientists have been able to do that because they understand the differences in molecular structure and in charge distribution. That's how they can create these medicines that can specifically target very specific membrane receptors to get a desired effect. What we learned in Chemistry 1 allows us to understand how an SSRI affects serotonin levels, but also how we can alter the molecular structure of molecules in order to target membrane receptors of cells by taking advantage of receptor specificity. So let's wrap up. To answer the question one more time, how does an SSRI like Prozac impact serotonin? It doesn't interact with serotonin directly, but rather with the protein SERT, which reuptakes serotonin. By blocking the SERT protein, SSRIs inhibit the reuptake of serotonin back into the neuron and therefore increase the concentration of serotonin in the synaptic cleft, allowing more time and concentration for the receiving cell membrane receptors to bind to the serotonin neurotransmitter and carry on with cell messaging. A few very good sources I highly recommend. I've listed them below as well. First off, there are some articles from the 1970s that will give you a very good rundown of exactly how this drug, Prozac, an SSRI, was viewed back in the 1970s when there were very few trials. However, in more recent years, there have been quite a few different side effects that have come up. And so, what's very interesting is to compare how the drug was marketed in the past versus how it was marketed in the current times. And I've listed both of those sources below. We also have sources that go over the molecular structure of Prozac, as well as a few interesting finds on how the different ion concentrations will affect the conformational change of the SERT protein. All of those are very interesting to look into as they're at the very forefront of depression and clinical medicine. What I also hope you understand is how important chemistry is in helping fight the battle against the current pandemic of depression that has taken over much of the world, and how it can be used to come up with the least evasive and most effective drugs that can help better the quality of life of so many patients around the world.